queue implementation using linked list data structure. We already discussed how the queue can be implemented using an array data structure. Although this technique of creating a queue or implementing a queue using array data structure is easy, the main drawback is that the array must be declared to have some fixed size. For example, if we allocate a size of an array, size of the queue is 20, in which I just want to store only 10 to 12 data elements alone in the queue. In such case, what would happen means the half of the space would go wasted, because the size allocated here is 20, but I want to store only 10 data elements. In such case, half of the memory space would go empty when it comes to an array structure. And in case I allocate only less memory location for a queue, and that might end up growing large and large. In such case, a lot of reallocations have to be done. So it would create a lot of memory overhead and it would consume a lot of time. Suppose in case the queue is very small one, and if you know the maximum size of the queue in advance, then the array data structure is going to be very easy. Array implementation of the queue is going to be very efficient. But what if the array size is not known in advance? In such case, you have to prefer the alternate data structure, alternate option, in where the linked list data structure can be used. Why? Because with the help of the linked list data structure, like you can use as many nodes you want, like the memory will not go wasted. Why? Because it is not having any fixed size here, because it has dynamic memory allocation. So linked list implementation of queue would help you to store as many elements you want in the queue without your memory locations go wasted. That is the major advantage of using the linked list data structure, and this is how the linked list structure would look like, linked list representation of queue would look like. And we all know, as we discussed in the previous videos, the queue has two ends, front end and rear end, in which insertions and deletions would take place. When it comes to insertion, always it would get performed at the rear end, and when it comes to deletion, it would always get performed at the front end, which means insertion can be performed at the last and deletion can be performed at the beginning. Why? Because if you imagine a normal queue, always the people who wants to join would join at the end, and the people who is leaving the queue would leave from the at the front end only. So it's actual queue structure. The real time queue is what is the actual queue data structure is. And if you take again, there are two basic operations here in the queue data structure as well, NQ and DQ. NQ means insertion and DQ means deletion. Let's discuss the pseudocode for both the operations insertion and deletion. As I discussed before, there are two pointers, two variables we are going to use here. One is a rear, and another one is front pointer, front variable. Rear end is the rear pointer would be always pointing the last node where insertion can be done, and front pointer would always be pointing the first node where the deletion can be done. Let's start writing the pseudocode. If you want to insert a new data element, for example, value 25 I want to insert newly into the queue. But now if I check, you just imagine that the queue is completely empty. There is no existing queue structure here. The queue is completely empty. So when the queue is completely empty, I have to, like always, whenever you want to create whenever you want to perform insertion in a linked list structure, you have to create one new node with two fields, right? I am creating a new node, and each node must have two fields, one to store the data and another one to store the address of the next node. You just imagine that the address of new node is new node itself. In such case, I just want to perform an insertion. I just want to insert a data element 25 into the queue. Since the new node is created, directly it can be written, right, in the place of new nodes, data field, you can directly write the value which you want to insert, right? Then address of new node is new node only. So in the place of new nodes data field, I can write the value which I want to insert, which is 25. After executing this statement, 25 would get written here in the place of data field of new node, right? Now the next thing is, I have to check whether the node which I am going to insert is going to act as the very first node in the queue structure, or already there are nodes in the queue structure and this is also going to be one among them. I have to check. If I check yes, my queue is completely empty, this is the very first node I am going to insert into the queue. In such case, definitely our front and rear would be pointing null, right? Where is your front and rear? My front and rear is null only because there are no other nodes in the queue. This is going to be the very first node. So initially you are going to initialize front and rear equals to null when the list is completely empty, right? Yes, my front and rear is pointing null only. In such case, you are supposed to set your front as well as rear equals to new node. The address of new node, right? The address of new node is new node only. Since my front and rear is equals to null because the list was completely empty, after inserting the new node, this node is going to act as a very first node in the list. So both my front and rear would be pointing the same node only when there is only one data element in the queue, right? So both front as well as rear would be pointing the new node only, right? Which means since this is the very first node, always first node's address would get stored under a separate variable which is called front or head or whatever. Here I am naming it as front. Since the very first node, both my front as well as rear would be pointing the same node. Address is new node, right? Now both my front and rear is pointing the new node only, which means under the front variable and rear variable I have stored the address of the new node. And since this is a very first node, what needs to be stored here in the place of next field of new node? Since there is no next node, it is very first node, right? So always since there is no next node, it would be having the null, right? So to fill null here, we are supposed to write this line. In the place of, since both front and rear is pointing the same node, write like this. Front next and rear next should hold the null value because there is no next node, right? Else cases, there are few elements in the list. I will create one more structure. Imagine this structure. Five, 10, 15, and always first node's address would be stored under the front variable and last node's address would be stored under the rear variable. Right? Imagine this structure. Now I want to insert a new value 25. As usual, create a new node. Yes, new node is created. After creating the new node, with the help of this statement, in the place of new node's data field, data can be written 25, and check whether front and rear is equals to null. No, front and rear is not equals to null. If so, you are supposed to execute these two statements. Since my front and rear is not equal to null, which means there are already data elements there in the list, I just want to insert my new data element into the queue now, right? So you have to go to the else part. Simple. There is already rear, right? The rear is pointing the last node. In the place of rear's next field, if you write the address of new node, these two would be connected. Yes or no, right? To write the new node's address over here in this field, we have to write a statement now. This node is pointed by the rear pointer, right? So shall we write like this? Rear's next equals to new node. After executing this statement, in the place of rear next, rear is pointing the node CC. In the place of rear's next, address of new node would come. Since address of new node has been written here, automatically these two nodes would be connected. The new node would get included into the chain of the queue, in the linked list queue, right? So in the place of rear's next field, I wrote the address of new node. And what next now? Since I have inserted a new node here, now my rear pointer should be pointing, always the rear pointer should be pointing the last node, right? After inserting this new node should act as a rear pointer. My rear pointer should be pointing the last node, which is the new node, right? Which means we are supposed to shift this rear from this node to this node, which means your rear pointer should hold the address of always the last node only, right? So to shift the rear, just write rear equals to new node, or you can write rear equal to rear next also can be written automatically. In the rear's next field new node is there, it would come to the new node, the rear pointer would automatically come to the new node. Otherwise in the place of rear you are just going to store the address of new node under the rear variable. It can be written like this also, rear equals to new node or rear equals to rear next also can be written to shift the rear pointer. After executing this statement, the rear pointer would come here. So finally the rear is here, which means the rear is pointing the last node. And what should come here? This field is still empty, right? New node's next field. New node's next field, new node is pointed by the rear only. Since I shifted under the rear, I stored the address of new node. It can be written like this. In the place of rear's next, null should come. Why? Because after inserting the new node into the list, new node is going to act as the last node and new node is pointed by the rear pointer. Since this is a last node, always in a linked list last node's next field should have a null pointer. So I am storing null in the place of rear's next. End if and end the pseudocode, because we have completed all the processes. We initiated the connection, we made the connection between these two nodes and we exchanged the addresses also. In this field we stored the address of the new node which we inserted, and in the place of new node's next field we filled the null, and also now this is acting as this last node, the new node is acting as a last node and this node is pointed by the rear pointer. Completed all the processes, so you can end the pseudocode. Next, let's see the pseudocode. Let's discuss the pseudocode for performing dequeue operation in the queue using linked list data structure. Dequeue is nothing but deletion. When it comes to deletion, always it must be performed at the front end, which means it should be always performed at the beginning of the queue structure only. Imagine this chain, this linked list structure. And always front pointer should hold the address of the starting node and the rear pointer should hold the address of the last node, and these are the data elements 5, 10, 15. Now let's perform the deletion. Now always when it comes to the queue, deletion can be performed only here. Deletion can be performed at the beginning, insertion can be done only at the end, right? Now we want to perform deletion, which means we want to delete the first node in the queue, and this is the queue. We represented the queue in a linked list structure. Let's start writing the pseudocode. The first case is when you want to perform the deletion, if the list is completely empty, you won't be able to perform the deletion, right? First you have to check whether front is equals to null. When the front would be null, when the list is completely empty, the front would be null, right? When front is equals to null, it has to print underflow. Else, simple, you just before you delete this, you create one temporary variable. Under the temporary variable, you can store this data element, the data element which you want to delete. Blindly you will not go and delete it, just you fetch the data, you will be fetching the data and use it for some other purposes, right? So you are fetching the data, which means you are disconnecting, you want to disconnect that node from the list. Before you disconnect the node from the queue, first you fetch the data element, you store it under some temporary variable. So under the temp I am storing the address or whatever, because finally we have to delete it. So if you want to store the data element can be stored under the temporary variable, which is temp equals to front data. If you want to store it, you can store it. And also this address also I am storing under another temporary variable, which is pointer. Under the pointer I am storing the address of front. Why? Because after disconnecting this node from the list, I just want to free the space. Which space I should free? I have to fetch the memory address and store it under another pointer, right? I am storing the data under one temporary variable and storing the address of the node under another temporary variable, which is pointer. Now simple, if you want to disconnect this node, simply you can shift the address, right? In the place of front, if you store the address of this node, since I want to disconnect this first node, which means I want to eliminate this from the chain. If you change the address of front from AA to BB, means definitely like this node would get disconnected and these two would be connected, which means in the existing list currently there are only 2 nodes, right. So, how to write BB here under the front variable? The where is BB? BB is stored in the place of front next, right. So, if you update your front as BB, since BB is stored in the place of front next field, you can write a statement like this: front equal to front next. If you check, front is AA, in the place of AA's next what is there? BB is there. After executing this statement, in the place of front BB would come. Since BB has been written, the connection, like these two will not be connected anymore and these two would be connected, which means this node got disconnected, right, because when it comes to the linked list representation, always first node's address must get stored under the separate variable, which is called front or head, it can be anything, but first node's address would be stored under separate variable because there is no previous node to the first node. So, that would be stored under the separate variable. That variable is front. Under the front we stored BB. Now, after shifting the address, now if you free this address space, this would get completely disconnected and also the memory space also would be free now, right. So, how to delete this space? If you want to delete this node completely from the memory location, you need to know which memory location you want to free first. Memory location already we stored under some other temporary variable which is called a pointer, right. Just free the pointer. After executing this statement, this node would get completely erased from this memory location AA. Now, if you check, completely the node got deleted, got disconnected and also we erased it also from the memory location, and currently if you check the queue, there are only 2 data elements. And if you check, since this is the very first node's address has been stored under the front variable and the rear variable is pointing the last address, which means address of the last node. Now, if you check, there are only 2 data elements and AA is completely empty, because we have to free the address space all the time. Why? Because so that the same memory location can be used by some other node. So, we have to completely erase the space. Since we have completed all the processes, you can end the pseudocode. This is how we are supposed to perform deletion in a queue using the linked list data structure. So, if you look at the pseudocode, this pseudocode is exactly the same of performing insertion at the end in singly linked list. If you check this pseudocode, performing deletion, it follows performing deletion at the beginning in singly linked list. So, if you are thorough with a linked list data structure, if you are thorough with all the types of linked list and how the insertion and deletion works over there, you will be able to understand the stack data structure and queue data structure easily. Also, even for graph and tree also we will be using the linked list data structure only. So, you need to be thorough with the linked list data structure and its pseudocode. It would be easy for you to understand the other data structures, stack, queues, graphs and trees. And when it comes to advantages, as usual, queue representation using linked list, there are advantages. The very first advantage is, as we all know, since we are using we are using linked list data structure, the main advantage is dynamic size. The linked list based implementation does not require any predefined size here, unlike arrays. The size of the queue can grow or shrink dynamically as elements are added or removed, since we are using linked list data structure. Second one is efficient memory usage, again due to its dynamic allocation. Memory is allocated as needed for each new element, potentially leading to more efficient memory usage compared to arrays that may allocate more memory than needed. And third is ease of insertion and deletion. Inserting an element at the end and removing an element from the beginning can be done in a constant time, which is going to take only big O of 1, because these operations involve only updating the pointers, right. So, it is going to take only big O of 1 complexity. And another one is no wasted space here. There is no need to reserve extra space here, because memory is only used for the actual elements in the queue, avoiding the issues of underutilized allocated memory that can occur with the array based implementations. And next are disadvantages. What are all the disadvantages? Let us check using the linked list data structure of queue. The very first one is memory overhead, because each element in the queue requires additional memory, right, for storing a pointer or for storing the address to the next element. This overhead can be significant for small elements. And the next drawback is non-contiguous memory location. Because linked list does not store elements in contiguous memory locations, which can lead to reduced cache performance and higher memory access time it would take compared to arrays. And third one is difficulty in indexing. Unlike arrays, direct access to an element at a specific position is not possible here in linked list in a constant time. If you want to access an element in a linked list structure, the traversal from right from the first node is actually required, which would lead to big O of n time complexity, because there is no index position here to point each and every node, right. So, if you want to access any of the node, again you have to start from the beginning only. It is a sequential access. You have to start from the beginning and you need to identify so and so node. Next are applications. Number one is for task scheduling. This queue data structure using linked list can be used. Queues are used in various scheduling algorithms such as round robin scheduling in operating systems, where processes are stored in a queue and processed in a cyclic order. And in BFS, breadth first search in graphs, this can be used to keep track of the nodes that need to be explored next in breadth first search, ensuring that the nodes are processed level by level. And for print spooling, print jobs, this can be used, because print jobs are managed using only queues where documents are added to the queue and printed in the order they were received. And in many producer consumer problems also this can be used. In multi-threaded environments, queues are used to manage the flow of data between the producer and consumer threads, ensuring that there is a synchronization and a proper data handling. Thank you.